Hi, good evening. Um, Myself Ananya. I'm a PhD scholar at IIT Delhi. So this is the doubt clearing session for week 8 lectures of aluminum-based alloys and metal matrix composites. So let's start today's class. If you have any doubt, you can ask. Otherwise, I'll start with my PPT.
No, ma'am. Actually, due to ill health, I was not able to go through the
The
lectures.
lectures.
I have
I have
only
only
gone
gone
through the
through the
first
first
three.
three. Okay. Okay, no problem. I'll go through one by one all the lectures uh, in the form of PPT. So let's see. If you have any doubt, you can interrupt in between and ask.
Sure,
Sure,
ma'am.
ma'am. So let me just present my screen. Just a moment. So these are the previous week's lecture topics, the grain refinement techniques, and then under grain refinement there were homogeneous nucleation, heterogeneous nucleation. For different nucleation, we have been taught about the surface energy, volume energy, melt inoculation, carbide boride theory, and peritectic reaction. So this week's lecture starts with the peritectic reaction. Before that, I have also mentioned about the dendritic formation in my last lecture. That was an extra topic I covered because it's important to know how the dendrites get formed during the solidification at the time of casting or any other process, because the dendrites are also acting as a nucleating site. You'll see later. So the week 8 topics were hypernucleation theory, solute theory, fading, poisoning, particle settling theory, mechanism of poisoning, grain refinement by vibration, grain boundary infiltration, orientation of high angle boundary aspect, relative motion velocity aspect, relative remelting, dendritic root, and the crystal ring. And then there was a topic of ultrasonic cavitation, electromagnetic cavitation, and severe plastic deformation. Under severe plastic deformation, there are several techniques which were not been taught briefly or not explained but only showed. So I'll be showing you the pictures respect to each severe plastic deformation techniques, and then dynamic recrystallization by SPD was started. And after this week's lectures, from week 9 the metal matrix composite will be started, because up to week 8 the discussion was on the metal alloys or aluminum metal alloys. So if you have any doubt till the alloy part, please ask me in today's class. In next class also you can ask me, but next class will be mostly on metal matrix composites. So let's start. First was about the peritectic reaction. So peritectic reaction, we have seen that for peritectic reaction for lower temperature we were getting the aluminum solidifying. So the melting point was changed due to the peritectic reaction. The aluminum 3Ti was acting as a nucleating site, but there were some limitations, like the percentage we needed to have the nucleating site was much more than the percentage which was added, but there are some solutions as well. So Al3Ti acts as the heterogeneous site for nucleation. We have also discussed like The heterogeneous are the most common one. Homogeneous nucleation is very rare. So we'll be talking about the heterogeneous only. So TiB2 will form shell around Al3Ti, and due to which the Al3Ti will get dissolved very easily, and if they are being dissolved, they will not they cannot act as a nucleating site anymore, so that is a problem. Grain refinement efficiency will decrease because due to Al3Ti, the grain refinement was taken place. So prevention of peritectic reaction will be present due to these things. So peritectic reaction will not be achieved that much, which is needed for the grain refinement or new grain growth. So this was the residue part of week 7. Now the next important topic is hypernucleation theory. So for hypernucleation theory, it was said like if one TiB2 element is sit over the lattice, if this is the surface of TiB2 and this is the Ti, then around or surrounding to this Ti, the particles which are present, the particles of Al, the motion of those Al particles will be suspended. How? Because surrounding to that Ti particle, the Al particles will try to get them arranged and make a type of lattice structure which is called a pseudo lattice. And for pseudolattice, it's something like these ales are arranged, and these ales are having restriction in their motion due to the restriction of motion of this aluminum particles. So this was all about the hypernucleation theory. So it's like from the pseudolattice we are getting new nucleus. So after some time, if we hold the material in that position, these new or pseudo arrangement will give rise to new nucleus which is needed for the grain refinement. But it will not be a long range lattice, because we can see wherever the TiB2 is present, everywhere this Ti particle will not be seated like this, and this will not form. So it's like wherever this is happening, wherever on the TiB2 surface, the Ti particle which is seated will be restricted, and the aluminiums are trying to get themselves arranged surrounding to them, or surrounding to that Ti, there only this pseudo lattice or pseudo things will take place and nucleation will happen. This is why this is not very much common, but this will happen and will act as a heterogeneous nucleation site. It will be a short range thing. So this was about the hypernucleation. The next one was solute theory. But before that, it's also important because in this picture also you can just visualize the Ti particle has sit over this surface, and surrounding to that this Al particles are getting arranged. So the size of these particles really matter. So if the size of the Ti particle is similar to Al, then only it will happen. So Ti is actually having similar or more or less same size like Al. This is why it's happening. Like zirconium or chromium doesn't have the same size like aluminium. This is why they do not participate in the hypernucleation theory, or they do not add the heterogeneous site for nucleation in hypernucleation due to the size difference. So this was taught in lecture 1. Lecture 2 included the solute theory. So before that, this picture you can see the carbide boride were given the were giving us the nucleation sites. Then peritectic theory we have seen Al3Ti particles were acting as the nucleation site. Then there is another theory, the duplex nucleation theory, where both the elements are playing similar role and together they are playing the role to have the or to bring the heterogeneous side. It's not been covered. And the next one is the peritectic Hulk theory. So it's like the peritectic theory. So just for example, so the next one was solute theory. So this theory suggested the nutrients and the segregation of solute particles. So there was one term introduced which is the growth restriction factor, GRF. Growth restriction factor. Okay. The growth, we do not need to have the growth, we only want the nucleation to happen, because if growth takes place now, the newly born particles will be bigger in size, will increase their size during growth, and we do not want that. This is why the growth restriction factor is important. We want the growth to be restricted, this is why we are dealing with this factor, this to be high to restrict the growth and to get the grain refinement, or to get the grains refined. So what are those? So it's like some solutes are there which promotes the growth restriction factor, or which promotes the growth, and which some are there which do not promote the growth. So there were one theory, like this was the curve related to that, where in x-axis there are NVP, which means by number of particles per unit volume, and this was NVG, which is number of grains per unit volume. And if this increases number of grains, then obviously the number of particles increases, or if the number of particles increases, vice versa. But it will not, it cannot increase up beyond certain limit, because then the particles will be so high in number that it will restrict the growth. So there is some reverse or adverse effect. So we want the particle or number of particle to be up to certain limit only, not crossing this limit, higher limit. So the growth rate is proportional to the GRM. Obviously, if the restriction factor is increasing, means the growth is less. So the growth has been restricted, so grain refinement is taking place. Next is there is one formula like GRF equal to MC dot K minus 1. I'm not going into the formulas, but the K is the concentration of solute by the concentration of the solute in liquid or solid composition. So let's come back to the GRF. At peritectic composition, the GRF factor will have one value for each particles. For example, for Ti, it's 31, for zirconium, it's 5, and for Cr, it's 0.5. Means for Ti, the growth restriction factor is high. Means the growth will be restricted, so grain refinement will be more in case of Ti. This is why we add Ti to the melted aluminium to have the grain refinement. But how much the Ti has been added, depending upon that also this growth restriction factor will be changed. So the next topic was fading.
Excuse me, ma'am.
Yes.
Ma'am, actually, I wanted to ask that this growth restriction factor depends upon the segregation, how much it's happening. Is it? Uh,
Segregation, and also there was one topic in last week's lecture, like even if we are providing some particles should have a low lattice mismatch with aluminum. In this week we have learned it has to be of similar size, because the mismatch in lattice, the size, the what say, the electronic configuration, their behavior, everything is responsible for the grain refinement, and depending upon which we have concluded that Ti has the ability to get the grain refinement.
Yes, ma'am, I got that. Ma'am, but can you explain like what exactly is segregation? I didn't understand it actually.
Okay, it's like TI leads to high GRF because high tendency of segregation. So the TI, this thing you are asking?
No, ma'am, I'm asking what exactly is segregation? Like,
Okay,
how
yeah.
does TI do
So
that?
the segregation means one thing is or the opposite word of the segregation is like the TI particles should not be agglomerated. So it's not it do, should not happen like the TI are sitting over here making some agglomerated things, and also the TI should not get dissolved inside the liquid, that it's also getting melted. It should act like the TI is present all over the melted region or all over the lattice or grains. Means they are segregated, means they are distributed uniformly and they are playing their role. They should not get agglomerated or they should not get dissolved. The in between meaning of these two.
Okay, ma'am, I understood.
Okay. Uh, yeah. So the next topic is fading. Fading Fading means solubility of Ti in liquid aluminium can go up to 0.25%. And although we are mixing just 0.01% Ti, but the solubility is very high. So it's like the Ti is giving us preferential site for the heterogeneous nucleation to happen, but we are mixing so much less amount of Ti that it will get dissolved. So we want this to be segregated. We want this to be distributed inside the metal, a liquid metal, and also not dissolved inside the material. It should sit like, if this is the liquid metal, it will sit like this. It will not get bonded with the other constituent elements, or it will not get dissolved in liquid. It will not get melted, or it will not should not get agglomerated in one point. Should not be like that. It should sit like it's not making any bonds to the other matrix or other grains. So we want that, but due to the high solubility of Ti, it's difficult to have that because we are mixing so much less amount of Ti. So Al3 Ti particles are not stable. Obviously, the stability will be hampered because of the high solubility, and this will lead to the dissolution of Ti particles or Al3 Ti that was mixed the master alloy inside the melted aluminium. The dissolution rate will depend upon the holding time, for how much time it's taking to get solidified as well. And like that way, Ti atoms are dissolved and then grain refinement will be hampered. So this is one problem related to Ti, which is called the fading. So fading can be avoided by optimize the holding time or the cooling rate or the melting point as well. So the next thing is particle settling theory. So obviously, if we do not want to,
Uh, Sorry, ma'am. Sorry to interrupt. Ma'am, like, how can we play with the melting point?
okay, the peritectic reaction. What was the peritectic reaction?
Ma'am, like that AL3 Ti was getting formed along with, like, it was the product. Yeah.
Yes. So it's like if you mix some constituent element in a solution, the melting point or the boiling point will also always get hampered. When you mix salt in water, the boiling point changes. If normally water gets boiled at 100 degrees centigrade, by mixing salt you can reduce it at 90 degree or 80 degree or so on. So that is we are playing. That is how we are playing with the melting point, no? Or the boiling point. This is the boiling point. So the similar concept. If you mix the alloying elements, they will uh, try to minimize the boiling or melting point of aluminum atom, because they are making some bonds with the aluminum. That will the bond will vibrate, and due to the vibration, the aluminum will get melted easily if it's been alloyed with something. So the for peritectic reaction, the temperature is also important now. Like if
Yes, ma'am.
we are mixing certain amount of Ti or titanium, then only the peritectic reaction starts. And due to the peritectic reaction or due to the constituent elements percentage, the peritectic temperature also changes. So it's the peritectic reaction also is related to the melting point or the solidus line or liquidus line. So if it is changing, then all the lines will get shifted at least a little amount. So it's like that. So the fading is already explained. So to restrict the fading, because fading is not important, is not needed for us, we want the fading to be avoided. So to avoid the fading, we want the particles to be um to not be settled down. We want that to be suspended inside the melting. So to for the particle to be suspended, we will be steering. So we'll steer. So when we mix some sugar in water, so we just stir it to get it dissolved inside the water. But that's another concept. But we don't want that sugar to be agglomerated and settled down below the water. That's why we stir it. The similar concept. So we want the particles to be suspended inside the metal, liquid metal. That's why we stir it. So the stirring will be not easy because the aluminum is having a temperature like 600, 700 degrees centigrade at the liquid state. So the steering can be done by many way, like normal mechanical steering tools at the time of stair casting or normal casting. Stair casting is one way. Otherwise, we can go for the ultrasonic or electromagnetic stirrer. So that is another thing. Let's have a look one by one. So particle suspension by steering is needed here. There is one graph like this, which is telling us about the effect of steering, that what will happen if we stop steering. So this is the fading zone, where if the things are getting faded, means if the Ti particles are getting dissolved inside the melted aluminum, then the grains will grow, because Ti is basically adding some grain refinement. So during this time the grain will grow, but we do not want that. So for a particular time we have to stir it. Also another thing is important, that is if you go for very high steering uh, velocity, na, there will be turbulence inside the melt. That will also be affect that will also affect the uh, microstructure and the solidification characteristics. So we do not want that as well. So the steering is very important and critical, that with how much velocity and with how much time we need to steer the liquid better. The next one is poisoning. So we want the Ti particle to be suspended in the liquid. So we want Ti particle to be like this, but we do not want to this things be like this. Why? Because these things really don't help in the heterogeneous nucleation, because these particles like zirconium, chromium, lithium or high level of Si, silicon, do not involve in the do not get involved into the nucleation process, and they do not provide any heterogeneous site for the nucleation, and they will hamper the process. But the adverse effect of this steering is, uh, along with titanium, this all particles will get suspended in the liquid. Before, titanium, zirconium, chromium, lithium, silicon, all the particles were getting faded out. But right now, due to steering, all the particles will get suspended. So that's a limitation or an adverse effect of steering, which is called poisoning. So these materials are acting like a poison to us because they are neither helping in the heterogeneous nucleation nor uh, just having like no effect. They are having some effect. So the ZrB2 will can make a coating of our TiB2, and ZrB2 is not good for the grain refinement, or substitution of Ti by Zr, that will make the ZrB2, because we want the TiB2 sometimes, but it will not happen if the Zr or zirconium is having bonded with boron. Changes in the lattice parameter, the orientation, if the mismatches increases, that will again hamper the nucleation sites, because if the lattice parameters and the orientation changes, then the TIs will not be successful in providing the heterogeneous sites. So that is another problem. Zr may displace the Ti from the particles or liquid interface. So it's like we are steering, we are trying to get all the particles suspended or Ti particles suspended. But due to the suspension of zirconium, it can just knock out the Ti from its place and it can sit over there. So that is one problem. So this poisoning is one problem related to the grain refinement techniques. The next thing is the grain refinement by melt vibration. Melt vibration means the steering we were doing with some mechanical tool. We can go for stair casting as well. But here we are not steering, but we are providing some external vibration through some external means, like the ultrasonic one or the electromagnetic one. So this is how we achieve the vibration or the steering effect inside the melt. Why we do so? If you can remember, in the last class we have been taught about these things. These are the dendritic arms. We have discussed that why the dendritic arms look like this and not like a triangle or a circular or cylindrical. So these are the dendritic structures. So these dendritic structures will just grow in size with time if the supercooling is taking place. But if this grows so much that at the tip portion there will be some small dendritic arm there, after one such vibration or steering effect, then this can get broken out, and this broken part will be now floating in the melt. Oh, it's having more temperature than the liquid melt. As I said that this portion is solidified, the portion I am just filling, this portion is solidified, but the interface is having much more temperature than the liquid. This is why it's called a supercooling. If supercooling has taken place, then this will be the scenario. Then even if the parts has been broken down and now it's floating in the melt, it will act as a heterogeneous site. But if it happens like the heterogeneous, the dendritic arm, which is now broken down and is floating in the melt, is so less in size that due to the high temperature in liquid it will just get melted again, then it cannot serve the purpose of grain refinement or the heterogeneous nucleation. So that is one problem. But the preferable thing is the most of the dendrites which are getting broken down, they will form they will float in the melt, and they will act as the heterogeneous site for more nucleations to happen. And this can happen like shear fracture mechanism, like the steering effect with some mechanical means. This can go with the grain boundary infiltration. So liquid infiltration in grain boundary induced by plastic bending of dendritic arms. So if we are just providing some bending motion or some shearing in the melted aluminium, then the dendrites will easily get broken down, and which is needed, which is preferred for us to have the heterogeneous nucleation. That is one thing. Then when the orientation of high angle boundary is more than 20 degree, the grain boundary energy could exceed that of the solid liquid interface by 2 times. So we have seen, like, if the this is the grain boundary and this is having the angle phi, so this will be surface energy of Sl. This is also the surface energy of Sl. And in the lower direction towards the another grain, there will be surface energy of Ss, because these are two grains. And this is the liquid part. So due to which the formula will come like this. And for the highest value of cos phi, it will look like this. So it signifies that the grain boundary energy between these two solids is equal to 2 times of the grain boundary energy in the interface region, which will promote this infiltration. This will add some more energy to the shearing that we are providing, and the breakage of this dendritic arms will be more and more, which is needed. Then relative motion or velocity of primary phase and the liquid phase should large enough for the dendritic arm bending to happen. Obviously, because you can visualize the thing, I cannot explain these things like that way, because we are having one casting or one mold in which we are having some solid and some dendritic arms. The arms will not this much in size, those are in micron level. This is the solidified part, this is the liquid part, and we are just providing some vibration so that there will be no turbulence in the melted region, but at the same time that high energized dendritic arms are getting broken. So we need to be very careful, because this vibration will be very critical to the whole process. So this is what been told. Remelting of dendritic root can also take place, as I said. The dendritic roots or the arms which are now broken, those can act as the heterogeneous site, which will be preferably happening, but it can also get melted again. That is a possibility, and there is a respective relation or equation. You can go through that. The steering can produce strong fluctuation in temperature and the composition, as I said, because the steering we were providing before for the suspension, to get the suspension of Ti particles, there also some poisoning was taking place, and now we are providing some steering to break down this dendritic roots. So both the steering velocity will be different, completely different. Both the process will be completely different, because to make the Ti particles suspended inside the metal, we have to have very high steering effect. But for the breakage of dendritic root, the steering should not be that much, otherwise all the things will be broken down and there will be turbulence. So this velocity of steering for different causes are critical, and it's a separate topic for study. There can be crystal drain. So crystal drain is also seen, like uh, crystal drain will happen if this is the mold, in which the aluminium is melted. Here the melted aluminium is present. The topic is crystal rain. Then, due to the chilling effect or due to the temperature gradient between the mold wall and the melted aluminium, the temperature between these two is very high, and due to which first the aluminium present surrounding the mold wall will first get solidified, and they will form the smaller grain because the temperature gradient is so high that the cooling rate will be very high, so they will get solidified. Okay, and they will block the root to get or to have the temperature transfer between the mold world and the melted aluminium. So this will be the thing, but at the same time this is having the melted aluminium, so there will be possibility of this small grains to get broken and drop in the melted aluminium or float in the melted aluminium, which are called as crystal rain. Means the droplet like small grains are getting broken and now floating inside the melted aluminium. So this is one thing, and these solidified grains will have the supercooling phenomena, due to which they will be having larger interfacial uh, temperature, and they will act as the heterogeneous nucleation site. So with respect to the surface of the crystal, the heterogeneous nucleation will start. Another thing is the small grains which are being formed here. These grains are made up of the aluminum alloy itself. It's not the particles which have been added to the melted material externally. So these are having the same crystal structure like the melted aluminum. So it will be very good to have those crystal grains to get the grain refinement, to get the heterogeneous nucleation, because it will be easy for them to get nucleated because of the very low mismatch between this crystal rain and the melted aluminium. Next technique is the ultrasonic cavitation. So,
Excuse me, ma'am.
yes, yes,
Ma'am, I have one question here.
yes.
Actually, we use shear near the mold wall. So, if we say at the early stage of solidification, uh, what will be the degree of undercooling? If we say, uh, is it large or small? Like, if we say about the undercooling process.
Okay, so you are saying cooling in with respect to the crystal rain or just normal case?
Ma'am, actually, I am asking about the crystal rain phenomena when it
Okay,
is happening.
so it's like that you just imagine this is the mold, and in the mold wall these grains are getting solidified very easily and very quickly at the early stage of the solidification, as you say, and this is having something temperature like 700 degrees centigrade, and these are solidified, means much lower than the 700 degrees centigrade or even lower than 660 degrees centigrade. So these will have undercooling because these can get melted very easily because their interfaces will not have that much high temperature. They are having temperature like the melted region. You understand what I'm trying to say? Because the heat which is present inside this melt has not been transferred anywhere. Before, for supercooling, it was like that this has been solidified already, and if there is some protrusion which is occurring here, it will grow like dendritic roots because there will be supercooling, because some heat transfer has taken place inside the melt. The melt is not having that much temperature, it's having somewhat around 660 degrees centigrade only, and it's lowering down its temperature with each step. and this is why the supercooling was taking place. But this is undercooling because uh, no problem. Anyhow, this grains has been formed, but the temperature is still 700 degrees centigrade. These grains will not have that ability to grow like the dendritic roots. It will not take place because they don't have that ability, because they don't have that uh, situation of having that supercooling. They will be undercooled. They will be cooled down, but their temperature will still be high, that they can get melted again in the melting, because there is no heat transfer taken place till now.
Yes, yes, ma'am. Understood. Actually, I got my answer. The same question I was asking before. Like in higher cooling rate, why we have more undercooling?
Okay.
Actually, from the definition of free energy that we were studying,
Yes.
like delta G is equal to delta G is directly proportional to the delta T, which is when we have
Because
the
the heat,
more
there is
undercooling,
no
that
time
is,
for the heat transfer, no?
yeah, yeah, yeah. Understood, ma'am. Yes,
Yes.
this explanation. Yeah, right, ma'am.
Or other way you can say, they has to transfer the heat to get solidified very fast. So it's not taking place the same way which is been done in case of slower cooling rate. The phenomena is different.
Mhm.
What is happening in supercooling, or with what is happening in quenching, and what is happening in case of the slower cooling rate.
Like any like the dendritic roots are being formed.
Yes.
Means it is just like a slow cooling. Yeah,
Yes.
yeah,
So
yes, ma'am. Thank you.
So ultrasonic cavitation is one way. So it's like we are just providing some ultrasonication in the melt. We cannot, you cannot see the ultrasonication from outside, but it will be felt by the melted aluminum only, or electromagnetic convection. The same way, some electromagnetic field you are creating, and due to which the Lorentz force is acting the role to create a huge pressure difference inside the melt, due to which that will be stirred or that will be vibrated. So these are two different things. This was up to lecture 3. Lecture 4, ultrasonic and the electromagnetic cavitation. So from lecture 4 we have been taught about the severe plastic deformation. So can anybody tell me why severe plastic deformation is needed? Because this thing was been taught earlier as well. Severe plastic.
Yeah, yes, ma'am. Actually, in process of CDRX, we need severe plastic deformation to refine the grains because more
Yes.
and more number of grains are forming inside the original grain.
Yes.
So we have a homogeneous type of nucleation in that case.
Yes. So if I tell you that this is grain number 1 and this is grain number 2, and in this, between these two grains, one protrusion has taken place and now it's acting as the grain number 3. So which type of dynamic recrystallization has taken place? Can you tell me?
Ma'am, this is DDRX.
Yes, this is DDRX. This has happened due to the which one of the
Uh,
dislocation?
it is it is at the grain boundary. So low angle grain boundary
Yes.
dislocation
So
arrangements.
it's due to the low angle grain boundaries. And if CDRX has happened, this will form like this. So CDRX we are talking about because CDRX adds some grain refinement inside the grain, and the amount of grain refinement is very high in case of CDRX than DDRX, and due to which we are talking about CDRX again here, and this will be formed by the high angle boundary. So severe plastic deformation means something in which we will not change the dimension of the material to be worked with, but will introduce a lot of strain inside the material in terms of the number of dislocations. So it's strange that we are introducing some strain, but we are not elongating it, because strain means delta L by delta L by L, right? Strain means percentage elongation. And here we are talking about severe plastic deformation, where we are introducing some strain, some plastic deformation in terms of the dislocation. This is why I have told you in one of my last classes that plastic deformation or strain means actually the number of dislocations you are adding to the material. Strain free grains means there is no dislocation. So strain taking place inside the material means the number of dislocation is increasing, and at the same time the dislocation is moving. The dislocation length is increasing. So this is why for severe plastic deformation, if you think about it, you'll understand that we are not introducing any strain ideally or practically. The delta L is zero here, the strain is zero, but still we are calling like we are introducing the strain in terms of increasing the dislocation density or the number of dislocations. So for dynamic recrystallization by SFD, we have seen that this severe plastic deformation is very much needed, because DDRX and CDRX needs the high dislocation density, and high dislocation density can be achieved via the severe plastic deformation only. So SFE for aluminum is very high, but at the same time we want the SFE to be high so that the dislocations can come fast and make themselves arranged in a particular way to get either CDRX or DDRX depending upon their energy of the boundary, either they are low angle or high angle. At the same time, when they have been arranged in a particular manner, the SFE we want to be low so that they do not cross slip or they do not move anymore, and they will sit at that particular arranged position and they cannot move further so that they can form the new grades. So this is one thing, the SFE for aluminium is 200 millijoule per m square. So cross slip is important thing for this. For first case we want the cross slip to be high, but for second stage we want the cross slip to be low, so that the dislocation arrangement should not move further. They will form the new grain. This is one type of nucleation. We have seen nucleation means new grain formation, and grain refinement means the nucleation is taking place in such a way that we are getting small grains. Because nucleation also encounters the grain growth, because just after the nucleation the grain will grow. So if I can somehow make the nucleation in such a way that the grain which are forming is having very less dimension, then even after some growth the grain will be of smaller dimension only, that we need for grain refinement for higher strength. So this was all about the up to lecture 5, and also it was shown some TEM and EBSD photographs of the microstructure. There the dislocation bands and the subgrains and the grains which are formed by dislocation was shown. Other than that, these are some severe plastic deformation tools. This is one high pressure torsion process. So plastic deformation we can provide by bending, by elongate it, by compress it, by providing shear or torsion. So this is what we are doing. We will just put some of the
Excuse me, ma'am. Sorry for
yes,
interruption.
yes,
I have
yes.
one question, ma'am. Yes. Ma'am, actually, you said that if the grains are nucleating, means anyhow it has to nucleate, or like means the for the for the solidification to take place,
Yes.
right? So
Yes.
if anyhow solidification is taking means grains are nucleating. So let's take example of CDRX and DDRX. So
Yes.
in which case we have a more fine grains in CDRX, right?
Yes.
Because of the lower size of the
Yes. Yes.
nucleations, right?
Yes.
Means for lower side of nucleations, we require high staking fault energy. In
We
case of
want.
CDRX, we have
Yes.
actually, in case of CDRX, we have high SFE. So if we have high SFE means there is a phenomena of cross slip. So if there is a cross slip means these dislocations are getting like moving very fast, and wherever they are finding nucleations, they will nucleate. Uh, Means for that, if we want to have more number of grains, means very fine grains, means it should have a high SFE, right?
Uh,
Can we
it's
say like this?
like, see,
Means,
we have introduced the, so
ma'am, actually, what I am not understanding is if we say nucleation, so
yes.
nucleation takes place everywhere,
Yes.
right? But then again, we say the small size of nucleation. So, means what you want to basically suggest in this too?
Okay, so let's
Like,
understand one thing first, that uh, we are dealing with or two state of material. Okay, in the last week we have dealt with the solid stage of material, where we were providing some plastic deformation to a solid matter, but here we are dealing with the liquid metal. So I have told you that if we are having one liquid metal, this liquid will have grains, will have the nucleation, because it has to get solidified anyhow, and solidification means the lattices are having less bond length in between them, and depending upon the different types of arrangement we are getting different grains. This was nucleation, but here we are dealing with the solid matter. We are having one aluminum rod already, or aluminum sheet, and I want to get more strength in this particular sheet. This is one sheet of aluminum, means it's solid. And here if we are providing some plastic deformation by just pressing it again and again, pressing releasing, or compressed and uh, just pulled out, so in that case I'm just uh, adding some dislocations inside this solid, and those dislocations are getting arranged by themselves to get either CDRX or DDRX. So these two are not similar, which you are talking about. The grain nucleation from solidification and the grain nucleation in case of severe plastic deformation. Up to lecture 3, it was been taught about the melted, melt aluminium. Like what we are, one problem is we are already having the solid aluminium, and in that solid we cannot melt it again. We just do the severe plastic deformation and strength increase. And another case, we are doing some casting, in which if you are making some casted product, there you can not add some severe plastic deformation, because you are having one geometry like this. Okay, now you cannot, you are just casting, you are making this geometry by casting. You cannot introduce any severe plastic deformation. No, you cannot add. So in that case, you have to solidify the material in such a way at the time of casting that the grain refinement will take place. So there are two aspects. Understood?
Yes, ma'am, I understood. Again, there is one question, ma'am,
Yes, yes.
related to my research area.
Yes.
Actually, I am moving for non-heat treatable alloys like 5 series alloys, and these are not heat treatable, means only we can play with the dislocations.
Yes.
That means only we can play with the severe plastic deformation, as you said, because we are going with solid state, not we are going not in melt, right? So there is no solidification in this case. So, ma'am, you said in previous lecture that uh, means what happens if we increase the temperature of these non-heat treatable alloys above the recrystallization temperature? Because what I was understanding that we are only playing with the solute in case of heat treatable, right?
Yes.
So we are hampering the motion of the dislocations by inserting solute atoms in between these. So right, but we can heat this non-heat treatable alloys also, right? So what happens if we heat it? Means why there is no chances of recovery in this case? Means
So,
actually I am not able to
did you
understand.
study about the non-heat treatable alloy and then melting point?
Actually, it is like okay, ma'am, please tell actually I have no idea about it. I
Okay,
think it is
so
below
actually,
660 degrees Celsius.
to be honest, I don't have any idea about the melting point of not heat treatable alloy. Only what I know is because not heat treatable alloys, I haven't seen very frequent application in my area as I'm also working in aluminium. So non-heat treatable alloy only you can play with the dislocation. This severe plastic deformation you can introduce, and severe plastic deformation doesn't encounter the solute atom movement that much because there the CDRX DDRX doesn't that much depend upon the solute atoms. They only depends upon the dislocation density and their movement. So I think if the number of solute atoms is not that much in case of any non-heat treatable alloy, then we can just introduce a lot of dislocation density inside it through the severe plastic deformation, and that dislocation density will play a role to have the DDRX CDRX depending upon the temperature. If we are hiring the temperature, the dislocation movement will be altered with respect to the temperature. So in that way we can I hope we can alter the CDRX or to DDRX to happen.
Ma'am, what else is there in non-heatable alloy?
What is, sorry?
Precipitations. That means because if we say 5 series alloys like 5052 or 5086,
Yes.
so these are non-heat treatable alloys,
Yes.
and we don't have any precipitations in this, like in 6 series or 7 series. So that means I am not understanding because we can also heat these alloys, like we are heating in 7 series or six
Yes.
series alloys, and we are getting precipitation hardening. But in
Yes.
this case, like non-heat treatable, we are not getting precipitation hardening; we are getting only strain hardening
Yes.
by severe plastic deformation. So what else in these alloys, in non-heatable alloys, which not allows these alloys for precipitation
Okay.
hardening, basically?
Okay. So
Because we can
actually,
also heat these alloys above
okay, okay.
recrystallization
I
temperature,
understand your
or we can
question.
get all this property as we were getting in precipitation
Yeah, I absolutely
hardening.
understand your question, but I really don't have that answer of this question. I also don't have that much idea about non-heat treatable alloy, but that is a very good question. I'll study about it and we'll get back to you in the next class for sure.
Sure, ma'am, sure.
I need to check some research papers for that because in Wikipedia or so you cannot find these things really. You have to
Uh,
go for some research which is currently going on this non-heat treatable alloys. I have seen papers on 5000 series, but I haven't read those papers yet ever.
Uh, sure, ma'am. Actually, yeah, in one of your lectures, you said like this. So actually, I was not able to understand. But
Yes.
why we are not going to play with the solute atoms in case of non-heatable alloys?
Yes.
But we are playing. We are playing in heatable alloys. Like we are getting different precipitations, and we have
Yes.
precipitation hardening and GP zones and all that. But why we cannot get in non-heatable? And we are only bounded to do like severe plastic deformation for grain refinement, but we are not going for the heat treatment process in these alloys,
Yes.
right,
It's
ma'am?
a, it's a
This is the questions
good
which.
question. So I'll go through. Sure.
Sure, ma'am. Thank you. Okay.
So let's have a look on the types or variety of severe plastic deformation, how we can uh, have those high dislocation density. Again, we are now talking about the solidified material. Till lecture 4, we were talking about the liquid material, that at the time of solidification how we can introduce the high dislocation density, uh, not dislocation, that their dislocation doesn't really have any role because there no dislocation is present. We were dealing with the liquid metal so that we can have the refined grains. Now we are adding some dislocations so that we can have the refined grains. So this is one technique of having torsion. So torsion means some shearing effect. So it can be either way, clockwise or anti-clockwise. But if I put some torsion repeatedly with a particular interval of time with uh, or in each direction with some time, means we are just rotating the specific specimen in clockwise and then anti-clockwise then clockwise in such a way that no strain is taking place inside the material. We are just going up to the upper yield point or up to the lower yield point just before starting the plastic deformation, and we are doing it repeatedly, then we can introduce the very high plastic deformation. Because if you see the stress strain curve, this looks like this, right? So there up to this point the material will increase its number of dislocation by which it restricts its motion, its strain inside it. The strain developed, which the strain which is developed inside the material till this much force can be restored right back after the removal of the force. But up to this point, it can be restored, but the Hooke's law is not valid. And from this point it will just increase its strength percentage elongation. So up to this point if we can just have that deformation, then it can be restored. So the deformation will not take place really, but we'll have a lot of dislocations present inside it, because up to this point what material does is it increases its number of dislocation inside the material to accommodate the strain which is occurring inside the material. So this is one thing. Similarly, this was the next topic. What is it called? This process? Anyone? You have gone through the lectures, no?
Yes, ma'am. It is equal channel angular
Yes.
pressing.
ECAP, equal channel angular pressing. So in this case, this is very important. We are just putting the thing, the putting the material from here, and by the use of this plunger, we are just making the material move inside it again and again, putting it here, putting it from here, and then pressing it towards this direction. We are just doing it again and again so that there will not be any percentage elongation, but lot of dislocation will be introduced. The next process is the cyclic extrusion compression. So there also we are just reducing the cross section in between, and again we are keeping the letting the material to get expanded again. So in that case we are compressing releasing, but no strain at the end. Here it's continuous cyclic bending. We are just adding some bending motion inside the material. We are just bending the sheet or the rod, but at the end we are just compensating the bending by providing the bending in opposite direction again and again to get the severe plastic deformation. This process is the repetitive corrugation and straightening. So we are just making this sort of waves inside the material, which is called the corrugation, and then straightening, and by which we are adding the dislocation. The next one is the accumulative roll bonding. This is also important in terms of the strain, because here you can say that strain is introduced like two sheets can be joined into one single sheet, in which a lot of dislocation will be present because the two sheets are now compressed making one sheet, so it's like a joining process as well. It will not be counted in severe plastic deformation because the plastic deformation is really taking place, and due to which, how should I say, why we are calling this sort of techniques as severe plastic deformation? Because even if we are not adding any plastic deformation practically, but we are adding so much dislocation to accommodate the force which is being introduced. But here it will not be called as severe plastic deformation, rather it will be called as plastic deformation, because it's like when some strains are introduced inside the material. Now, strain introduced means accommodating the load which has been applied externally. Now, load accommodation can take place by two ways. One is dislocation density high हो जाए, या फिर by having a real percentage elongation. Either it's lengthening, or we are just increasing the length of the material or increasing the dimension of the material, by which we can add the plastic deformation, or we can add lot of dislocation, we can introduce a lot of dislocation. So when we introduce a lot of dislocation without any strain.
Ma'am, but here, uh, like we are basically mechanically causing the surface to get joined.
Yes.
So, like, it's also sort of, ma'am, severe plastic deformation only, no?
So that's what I'm trying to explain. Severe it is a severe plastic deformation. But if I ask you in terms of mechanical or metallurgical terms that what is severe plastic deformation, it's like when you do not get any percentage elongation in the material, but you are having a lot of strain inside it. स्ट्रेन मतलब तो हमको पता है कि स्ट्रेन मतलब परसेंटेज इलोंगेशन होता है, बचपन से तो वही सीखे है ना. बट हियर वी हैव बीन लर्नड लाइक we are introducing strain without any percentage elongation. How? Just increasing the dislocation density. So that's what I have written here. When you are, so you have applied some load to the material. So if the material is not breaking, here one assumption is like there is no breakage in the material, there is no fracture in the material, then the material will try to accommodate that externally applied load. How it can accommodate? It can just add some dislocation and add the length also. Means there will be some plastic deformation like percentage elongation with the high dislocation density. Or there is a new thing which we have learned today, that without adding any percentage elongation, we can have a lot more number of dislocations. So the if the dislocation here is number of dislocation is 100, here it will be 1000, because we are not having any strain. But in this case of what is it called, the accumulative roll bonding, ARB, for this process we are adapting this one. We are having high dislocation density and we are having some percentage elongation as well. So we are having the true meaning of plastic deformation. This is why it will not be called as severe plastic deformation. It is severe plastic deformation. We are providing severe plastic deformation, but the meaning of severe here is not playing the actual role. Means what we understand by severe is very high value. So yeah, we are providing very high value of plastic deformation, but in terms of metallurgy we will not call it as severe plastic deformation, because severe plastic deformation doesn't have any percentage elongation. So could I explain it to you all? Is it okay for you? what I have explained right now?
Yes, ma'am.
Okay. So severe plastic deformation is something which is very uh, critical because it's difficult to visualize that we are putting so much force in a material but still we are not having any percentage elongation, rather at the same time we are having so much high dislocation density. So this is why the ARB process will not be called as severe plastic deformation in terms of metallurgy. The last process was friction stir welding or friction stir processing, in which the friction stir casting, welding, additive manufacturing, all the processes are there. So it's friction stir processing where you'll introduce a plunge and then there will be a shoulder which you are just spinning the shoulder, and there will be, due to the spinning of the shoulder, two material will be joined. So here we are not deforming the material anyhow. We are deforming the material, but the length and the weight and the all the things are similar. For two sheets, we are just joining two sheets. So at the time of joining, we are not melting the material. At the solid state, we are joining. So it's also called as solid state joining. And using this concept, additive manufacturing is also having one category of friction stir aim process. So this is all about the week 8 lecture series is still.
Ma'am, ma'am, actually, can you explain the exact difference between processing and welding, like in case of friction steel?
Okay, here it's, I don't feel there is any difference because for processing also it's like, if you're, so yeah, suppose you are having one sheet and in this sheet you want a severe plastic deformation. So what you can do is you have to have no percentage elongation for severe plastic deformation, that we know. So I cannot introduce any percentage elongation but I want to have some finer grains by severe plastic deformation. There what I can do is I can do this friction stir processing. But this friction stir processing concept is used for the friction stir welding as well. So there only the tool will be present which will rotate. This type of tools will just rotate in the joint, in the at the joining of two sheets. That will be called as friction stir welding. So when you will be dealing with one material, you can call it friction stir processing. But even but anyhow, the friction stir processing only counts the friction stir welding. For normal material, you won't go with the friction stir processing until unless you have to join two solid materials at solid state. Is it okay?
Ma'am, can we say like this? If there is friction steel processing, means there is no percentage elongation in a material, and at that case we have severe plastic deformation. But
Yes.
if else we are joining these two material, so at that case there is a material flow from one material to the
Yes.
another
Yes.
material. So there is a plastic deformation.
Yes.
So what I understand from this lecture, actually I was a bit confused about the difference between these two. So I think there is a difference in case of, for one case we can say plastic deformation if we are joining the two plates, and for this case we can say only severe plastic deformation because less percentage elongation. Can
Yes,
I say like
and
this?
yeah, yeah, you can say, but there is another thing because after you are, when you are rotating this plunger, which is attached with the shoulder, now the surface of the material at the end of the process will be hampered. So there will be some plastic deformation in the material if you are going for friction stir processing of one solid.
Ma'am, actually I am talking about the final dimension of the
Yeah, the final
sample.
dimension will be same,
It will,
but there will be some
that's what.
change in the surface of where you have used the friction stir processing or the friction stir tool.
Okay, so we were talking about the final dimension for severe plastic,
Yes,
as you
the
said in
final dimension. So you can
final
do
dimension
like,
only.
if you just go by from this way, from this way to that way, and then if you come back from that way to this way following the same path, then you can somehow avoid that surface roughness and the surface properties, because after the end of the process now it will look like this, the surface. And if you go like this again, then you can somehow avoid that thing. But it's difficult to say, this type of friction stir processing as severe plastic deformation. I'll rather call it as plastic deformation.
Okay. Why this plastic deformation? Because there is no
Because
change.
yeah,
There is a
the
change in dimension.
even you can say even the final dimension is same, but there will be some alteration in the upper surface, no? That can alter the dimension like in micrometer, but there can be some change. So you can anyhow call it as severe plastic deformation as well.
Uh, okay. And ma'am, if we are applying some axial force, right?
Yes.
So what this axial force is means if we are plunging
Okay,
the
so
tool in the
you
workpiece.
have to enter the tool inside the material, na, this much region. So you have to press the tool and rotate the tool. You have to press it and then rotate it. At the same time, these two forces are acting.
Okay, means the pressing the tool means the tool shoulder is just moving towards the
Yes.
workpiece. Means
Yes.
there is some plunge there. That means the should if the pin will go and along with the pin, the shoulder will also enter into the
Yes.
workpiece if we have more force, right?
Yes.
Okay, ma'am, can we measure this force? How much force we are applying?
Yeah, so this force is optimized. You cannot put a lot of force, then there will be a real plastic deformation. Na? The material can
Uh, uh,
just break out.
ma'am, I'm asking, can we measure this force? How much force we are applying?
We
Can
put
we
this
measure it?
force. Now, why to measure the force? We put the force. We decide the force, and then we put it.
Yeah, that's what I was thinking is before that if I was able to calculate the force at what force means how much force I am applying over the workpiece by the
Okay.
tool. So accordingly, I can go with the some characterization technique and that will be that force will have a some parameter that can be optimized by reading some characterization
Yes, you
after
have to
the welding
optimize the
processes.
force.
That's what.
See, the plunger that is attached with a manipulator, na, and we are deciding the force with respect to the rotational force as well. So we are calculating both the force, that how much velocity we need to put to the rotational movement of the tool, and how much force we need to put, because due to the rotational movement there will be some force induces. So all the forces should have a resultant value that will create the impact on the material of the fixture stir processing, and we are optimizing it to get different microstructure. So yes, we can change or alter the force with respect to the microstructure we want.
Ma'am, yes, we can change, but how to get this force means the magnitude of this force means can we have some instrument that we can enter at that place?
Force, yeah,
That means
there I
that we
don't
can
remember
use.
the exact name, but there are some sensing what say some sensing machines which can sense the force measurement sensors. There are some.
Okay, right. Actually, I will
There are
search
some
it, ma'am, and then I will
accelerometer
ask you.
which measures the acceleration. There also you can
Okay,
get the force.
okay, okay.
Yeah.
Yeah, yes, ma'am.
Okay.
Yeah.
So now let's have a quick look on the MCQ questions that I have from the current semester and the previous semester. So last day we haven't discussed about the questions or MCQ questions. So due to which I am having a lot of MCQ today. We'll start with the previous year questions and then we'll come back to the current year questions that you have already performed in your exam. So the first I want you guys to answer. So please unmute yourself and answer. So for week 7, the first question is the critical size of nucleus in a homogeneous nucleation is. No? It's directly proportional to surface tension. The critical nuclei radius R star is the minimum size needed for growth to continue or maximum size up to which a grain can what is it?
It's the
It
minimum.
is the minimum size needed for the growth to
Yes,
continue.
to start or to grow, you can say. And it's the same for both heterogeneous and homogeneous nucleation, because the R star really doesn't depend upon the heterogeneous homogeneous. However, the free energy and all those things will get altered, may get altered for these two cases, because these two cases have very different scenario. The next question is the critical free energy delta G star for a heterogeneous nucleation is than that for homogeneous nucleation.
Is lower than homogeneous nucleation.
Yes, it's lower. In solidification experiment, an aluminum billet is heated to 700 degrees centigrade and to be undercooled. As the degree of undercooling increases,
Grain size becomes finer.
the solidification rate first increases, the grain size becomes finer. One second. Just a second. Okay. Yeah. Consider the following statements. Metal do not solidify exactly at the melting temperature. Solidification occurs at the melting temperature slightly above the melting point, or the temperature slightly above the melting point. At melting point, the driving force is zero and a negative delta G is necessary to drive the solidification.
Ma'am, at melting point, the driving force is zero, delta G is zero, and a negative delta G is necessary to drive the solidification.
So at melting point, the driving force
Uh,
is zero, the delta G is negative, and the melts do not solidify exactly at the melting temperature. So when the melting temp when it's if it's 660 degrees centigrade, then from 659 it will start solidification. The solidification will start, and slowly after passing the solidus line it will get solidified. Next is this picture, what it depicts. What do you think? Undercooling means at the mold wall the things are getting solidified, the melts.
at first, option one,
Yes.
there is high degree of undercooling.
Yes. It's uh, the things, the delta G plus minus is going rapidly. The nucleation in solid is most in most cases is governed by, it's easy. What should be the answer? It's easy, na?
Actually, it is homogeneous.
It should be heterogeneous, na? Homogeneous is the rare case where without any help the things are nucleating the melted aluminium. because
Yes,
every
yes,
time
ma'am.
the nucleation uh, require a particular surface that will act as a preferred site for the nucleation, so it will be heterogeneous. The next one is if the delta G star heterogeneous is given as 10 kg 10 kilojoule per mole, uh, and delta G star what is it is given as this, calculate the shape factor. It's only mole.
Yeah, it is the ratio. It is, I think it is the ratio 1.5, I think, 15 by 10.
It's if it's the
No,
ratio, how much is coming?
1 point.
It's 0.667. You can check the formula. Yeah.
Okay, yes, ma'am. 10 by 15.
By homogeneous, is it?
Sorry.
Is it like heterogeneous by homogeneous for delta G star?
Yes.
Yes, it is 0.667, 10 by 15.
Yes. 10 by 15. Then, which of the following properties can be enhanced by grain refinement?
Creep
It is
strength,
fatigue strength, fracture,
fracture strength.
fatigue fracture, uh,
Creep
all,
is
all
having the
above.
adverse effect. The fatigue and
Creep,
fracture we can enhance.
Yeah, creep resistance can be increased.
Yeah.
ma'am, couldn't be corrosion resistance.
It's only the fracture and the fatigue.
Uh, Ma'am, why not corrosion resistance?
Corrosion resistance can be added or can be increased by the adding of the solute atoms, but it's not necessary that for grain refinement it will increase, because if you think that in case of refinement the grain number of grain is increasing, so the intergranular boundary those things are increasing, so they may not increase the corrosion resistance. It can happen that the grain boundaries are getting corroded, so if the grain bound number of grain boundary is high, then the corrosion will be high. How it will resist the corrosion?
Okay, ma'am.
Then during okay, it's fatigue and fracture. During heterogeneous nucleation, if the contact angle tends to 90-degree, calculate the shape factor. Shape factor equation I think you are already having. So I'm not
Zero
going.
point 0.5.
Yeah.
0.5.
So the next question is, it's the previous year assignment for week 8. Let's see from question number 1. Melt inoculation method is an example of what?
Heterogeneous nucleation.
Heterogeneous nucleation.
For the melt inoculation method to be effective, what will be the possible case?
The grain refiner should form intermetallic secondary phases.
Yes. So the intermetallics now will act as the heterogeneous nucleation site. While using TiB2, there is it's printed two types. As grain refining agent for an aluminum alloy, select the optimum condition to obtain plate-like aluminite. It was given in the last week, I think. What should be the answer?
I think, ma'am, slow cooling from high temperature. I think.
Yes, slow cooling from high temperature. Statement 1, there is two statements. So 0001 plane of ALB2, again two times printed, has lower mismatch with the 111 plane of alpha aluminium. Statement 2 is this ALB2 phase acts like gain refinement.
Statement one is true. Statement two is false. If it
Yes. So it's the third option. Statement 1 alone is correct.
Ma'am, can you go back to third question, please?
Yes.
Uh, Ma'am, actually, I'm not able to get it. Like, why this plate-like aluminides will be formed from slow cooling?
Okay. It's discussed in the last week, I think, that it's the morphology that you generally get. There is no particular reason like only plate like will form. It's like if it's TiB2 and if you are doing slow cooling from high temperature, plate like aluminides will form. Or if it's Al3Ti, then something else will form. Some other structure will form. They just what's it? They just follow that particular shape. Like for Si, it's needle-like shape. Now for alpha aluminum, they follow a needle-like shape. So why is it so? There is no such reason. They just form those type of shapes. It's generally seen that if there is alpha aluminum, they will form needle-like structure. Just similar case, the TiB2 will form the plate-like structures.
Okay, so ma'am, my the suppose if a cubic type of aluminide were to form,
Yes.
then like what would be the condition?
Okay, that depends upon the material. That TiB2 is forming the plate-like. It's not like that Al3Ti will also form plate-like when it's cooled down slowly from high temperature.
Okay, okay, okay. So means like apart from this cooling rate, it depends on the
Material, yes.
heterogeneous nucleating particle.
Yeah, any particle. When you see the aluminum microstructure, now you often see or observe a needle like alpha aluminum. But if you are dealing with stainless steel, the ferrous or those things will not look like needle shape at the first stage. So it depends upon the material as well. They may look like needle as well. That will be their characteristics. It's not like if they're alpha, they are at pure stage, then they will also always look like needle. It's not like that. It depends upon the material how they generally follow, how they generally form the lattices.
Ma'am, I have one question in this regard. If we have a slow cooling with lower temperature, then we are having blocky type structure.
Yes.
And if we have
From
a slow cooling at higher temperature,
there
we
is
have plate type.
there is a relative thing. Okay, you just imagine that from low temperature you are doing slow cooling, and from higher temperature you are doing slow cooling. So
Yes.
relatively, if you compare these two phenomena or these two situation relatively, then the cooling rate from a high temperature will be much more slower than the low temperature. Or you can say vice versa. Like it's like 50 degree centigrade water you are cooling and a 100-degree centigrade water you are cooling. You cannot say that the 50-degree centigrade water will be cooled down fast because the starting temperature is different. But if you draw a relative comparison, then obviously the 50-degree centigrade water will take lesser time to get cooled down. So the cooling rate is fast, we can say, relatively. But the cooling rate is similar. Or else you can say the cooling rate is fast. It is slow cooling, but when it is high temperature, it will be slower. But at the same time, uh, it's possible when the other conditions are fixed. The temperature gradient also plays a role. So the situation may be vice versa as well. That's why I told. You can say when the temperature gradient is more, the heat transfer will be more, so the cooling will be faster. You can say like that also. So depending upon that, the formation of these things are different. The shapes which are being formed is different.
Actually, in relative form, if we are taking means
So yeah.
100 to, let's take example, 100 to room temperature and 50 to room temperature. So there is a high gradient. High gradient means fast cool rate. And if we say like means if we say if we are having 100 degrees Celsius temperature and now we are getting 19 degree, so the relative terms if we are telling means there is low gradient.
Yes. Another thing also you can say, if you consider that the plate-like structure is forming like blocky type structure when the low temperature, it's low, the temperature is low where we have started the cooling, and at the same time the cooling is a slow cooling, then you can say it will take more time to get cooled down. So there is more grain growth. This is why it's blocky type. The thickness has increased, but when it is from high temperature, the cooling rate is higher than that of low temperature. So this is why the thickness is lower. We are calling it as plate type. So I think this way it is more clear.
Yes, ma'am. Now it is
Yes?
clear.
Yeah.
Yes,
So
yeah.
I should have drawn this example first. So its blocky type means the thickness has increased. The grain growth has taken place due to the slower cooling. So it's relative to each other, and also it's like plate like or blocky type. You can consider it as a structure generally observed structure of TiB2. You can say like the AL3 Ti may also form like the facets in plate or in blocky type. Yeah, so it can be
Okay, that means
spelled.
there is, and that means there is no grain growth in blocky type. Means we cannot say that grain is growing in case of blocky type, right? In clay type we have a high thickness. You are telling
No, for blocky type we are
because
having
at
high
higher temperature
thickness.
slower cooling. At high temperature we are cooling slow. That means there will be a chances of grain growth, right?
No, 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 no. I am comparing these two situations, the slow cooling from low temperature and slow cooling for high temperature. Now you
Yes.
eliminated this term slow cooling because now the cooling rate is fixed now. Both the cases we are having slow
Okay.
cooling. So we cannot play with this slow word. So now it's from either low temperature or higher temperature. Now if we compare these two situations, then the cooling rate will be relatively higher in case of high temperature because of the high temperature gradient. And
Yes.
there we'll get plate type where the thickness is not that much, means the grain growth has not been taking place that much. But in case of lower temperature cooling, it's slow, but it's relatively slower than high temperature one. So it will
Understood.
grow more. Understood?
Yeah. Understood.
Okay.
Yes.
So the next
Okay, ma'am.
one, yes, yes.
Ma'am, regarding the fourth question, I had a doubt. In case when the this registry between two facets is low, then that's when it's better for grain refinement. No, like, isn't it better? Like,
It's
so
better for the heterogeneous nucleation.
yes, but isn't it acting as a grain refiner? Like,
The heterogeneous nucleation will take place, but you cannot comment on the growth of that nucleating thing, because if growth is taking place, then the refinement will not take place. So grain refiner means we have assumed that it's having some higher cooling rate, because when you refine the grain na, means there will be some nucleating sites we are providing, and there the nucleation will be faster than the other melted portion. It will be faster, but if you are holding it for some more time, it will grow. the nucleated new grain will grow. So you cannot comment on that directly that the grain refinement will also take place. Yes, obviously AlB2 acts as the grain refiner in terms of providing the heterogeneous nucleating site.
Ma'am, but in case of AL3TI, when we say that 112 plane and 111 plane, we are just directly saying it like AL3TI is a
Here
good.
also we can directly say it like the AlB2 is acting as the refinement, grain refiner. But here the see, if I have appeared for this test, I may also tick for the both statements are correct, because we are dealing with this material, we are adding this type of things to just get the green refinement. But maybe they have set the question like the refinement will also dependent upon the time for which we are holding the material.
Also, ma'am, the lower the mismatch, as you said, the chances for growth are also there. So, is it because of that that the second option is not right?
Lower mismatch, apart from growth, first the nucleation will take place, no? So lower
Yes,
mismatch first will promote the nucleation, after that the grain will grow if there is sufficient time. So you need to
yes, ma'am.
understand this thing. The growth needs sufficient time, but the nucleation needs a proper heterogeneous site. Both
Yes, ma'am.
the requirement of these two things are different, although they are taking place simultaneously, although there are some assumption behind it, but the requirement for these two things to take place is different. So I think up to
Understood.
4 it's clear now. So we can go for question number 5. Severe plastic
Uh,
deformation. Yes.
Ma'am, I'm having one doubt here.
Yes, yes.
Ma'am, actually, in assignment, it was one question in week seven assignment. The grain refinement efficiency of TiB2 in aluminum alloys can sometimes be relatively low due to what? So, ma'am, if the grain efficiency of TiB2 is low, means we have low wettability, is right. And
TiB2, I
there
think.
is one option also, high this registry plane,
Okay.
because if this registry is low means uh, there is a less misalignment
Yes.
between these surfaces.
So TiB2
So,
is helping or not helping? What was the question?
question was the grain refinement efficiency of TiB2 in aluminum alloy can sometimes be relatively low. So, ये low क्यों होता है?
Because
So,
TiB2 form the shell structure around Al3Ti, na? The Al3Ti is the main component which acts as the heterogeneous site. We
no,
have
actually जो मैम जो option था it was low wettability
yes.
and low this registry plane.
Okay. I think it
So
should be low weightability, na? Or
it is low wettability is right,
yeah.
but
So low
if
distress
efficient,
because if the lattice mismatch is very low, then it will
yes.
act as the grain refinement. But at the same time, TiB2 also creates some problem to the Al3Ti.
So what about what we can comment in this registry plane? It should be high or low
Should be low.
if
The
efficiency
mismatch should be
decreases.
low
Mismatch should be low. Why?
because if the mismatch is low, na, then only
Yes.
the things can get attached. The melted aluminium can get attached to that solid particle, to that
Mm.
TiB2 to nucleate it.
Uh, yeah. Then there is the grain refinement, right?
Yes.
Yeah. So, but grain refinement is low in which case? So, grain refinement is low in low wettability and high dysregistry plane, correct?
Low weightability and low mismatch. High weightability and low mismatch. Weightability should be high, na?
I
It
think there
should
is
be the dilution between this is the TiB2.
wettability means I am understanding that is contact angle. Means contact angle should be low.
Yes. If the mismatch means if this is the lattice orientation and this melted aluminum is also having this lattice orientation, then this is the preferable condition. And also if this is the scenario, like this is the surface and this surface is making this sort of angle like this, so the dilution is more. But at the case
Okay.
of this thing, if this is like this, the angle will be lower, so it will be easy for the grain to form quickly, to form the nucleus or to nucleate.
Means grain refinement efficiency increases in low disk registry, right?
Yes.
But there is wrong answer. It is. If actually question was कि when it will be low, ये low कब होगा?
So
So
did you
that's
see,
the answer.
could you see the
High disk
answer, right
registry.
answer?
Answer is low wettability and low disk registry plane
Yeah, low wettability. Okay. So low
and
wettability
low
means
disk
this
registry.
thing ना, low distress तो समझ में आ गया कि ये कि मिसमैच इज लो. लो वेटेबिलिटी
मैम
मीन्स
मिस
ये अगर ज्यादा
मैम
हो गया ना.
मिसमैच मैम अगर मिसमैच लो होगा तो ग्रेन रिफाइनमेंट एफिशिएंसी ज्यादा नहीं होगा बिकॉज देयर इज अ चांसेस ऑफ न्यूक्लिएशन.
हाँ, न्यूक्लिएशन के लिए तो ज्यादा मतलब डिस्टेंसिटी लो ही होनी चाहिए ना.
हाँ बट मैम क्वेश्चन ये है कि ग्रेन रिफाइनमेंट एफिशिएंसी ऑफ TiB2 इन एल्यूमिनियम एलॉय कैन समटाइम्स बी रिलेटिवली लो ड्यू टू मतलब लो कब होगा ये क्वेश्चन है. तो
अच्छा, लो कब
फॉर
होगा.
लो हाँ हाँ तो फॉर
जब
लो देर इज हाई
हाँ,
डिस
जब
रजिस्ट्री
लैटिस
प्लेन ना
मिसमैच बढ़ जाएगा, हाँ इधर पे
बढ़
लोड
जाएगा
वगैरह
मीन्स हाई
लगेगा.
डिस रजिस्ट्री बट आफ्टर इज लो डिस रजिस्ट्री प्लेन एक्चुअली एक्सेप्टेड आंसर
हाँ.
वी गॉट द आंसर तो
ओके.
वहाँ पे लो डिस रजिस्ट्री प्लेन है.
पर ये तो हाई होनी चाहिए.
So that was the
Okay, I
conclusion.
also
I
don't
got
have
the
any
answer.
contact so that I can ask.
Actually, it is week 7 assignment question number 9.
Okay,
So
okay.
please check once, ma'am, right?
Okay, this question I remember. Okay, I'll see what is the answer and what is the possible, what can be the possible reason. Otherwise, it can happen that they have put a wrong answer somehow. It may also happen, na? But I'll check. There is a high
Sure,
chance of
ma'am.
having right answer only. I'll check. Okay. So the next question is okay. This thing is sorted. I ask? Okay, I didn't ask. I forgot this question. Severe plastic deformation involves grain refinement and high strain with negligible shape change. Means negligible percentage elongation with high dislocation density. So the sixth question is, which of the following is not severe plastic deformation technique?
Accumulative roll bonding and uniaxial forging.
It's uniaxial forging only, but the accumulative roll bonding is also not a severe plastic deformation technique. Okay. Okay. Next is, select the element that act against grain refinement by melt inoculation method.
Titanium and boron. First and third.
That act against the grain refinement.
Against is apart from that. Silicon,
Lithium and
nickel, and
chromium.
bromine.
And silicon as well.
Yes.
The next question is, as the concentration of the solute in the solid and the solid liquid interface increases, the equilibrium partition coefficient K increase, decrease, remain constant, independent.
Ma'am, it should be constant only. Ma'am, because like equilibrium partition coefficient depends upon the solubility in liquid divided by solubility in solid. So
I
their
think
solubility.
it increases. I think K is
At
equal
the
to
same
CS by
time,
CL.
the K defines the concentration of solute by the concentration of liquid. Now, so if the solute in the solid at solid liquid interface increases, the K should also increase. है ना? Is it clear?
Yes, ma'am.
Okay. So the next question is statement 1. In the crystal grain phenomena, the crystal nuclei form on the mold wall. Statement 2 says large degree of undercooling is observed on the mold wall. Which one is correct or wrong or what?
My
Both
option
are
is both the
correct.
statement are correct, and two is the reason for statement one.
Both the statements are correct and 2 is the reason for the statement 1 because of the large degree of undercooling. The last question is with respect to the dendritic formation mechanism in nucleation of new grains, choose the incorrect statements. At the root of the dendrites, there is a localized decrease in temperature due to compositional fluctuation. Remelting can occur at the root of dendrites due to the localized elevation in temperature. Stirring the metal or melt can lead to the fracture of the dendritic arms. Liquid infiltration in the interdendritic arm spacing can lead to splitting of the dendritic arms under suitable conditions. I think it's pretty easy again.
One only.
Yes, the one is incorrect because in the interface of the dendritic root, the temperature is much higher than the melt temperature. So that's about the previous year questions.
Ma'am, can you go in the last slide?
Yes,
Uh,
last Friday. This one. Yeah.
yeah, ma'am, this fourth point that liquid infiltration in the interdendritic arm spacing can lead to the splitting of dendrite arms.
Yes.
Uh, I'm not able to imagine it, ma'am. Can you like explain it?
Okay. लिक्विड इनफिल्ट्रेशन का मतलब क्या समझ में आता है?
Um, Ma'am, like the liquid which is like leftover between the arms of the dendrites.
Yes. So the liquid is having uh, you first tell me that there is a temperature difference between the liquid present in between the inter spacing of the dendritic arms and temperature between different difference between the dendritic arm. So there is a huge temperature gradient. So in the dendritic arm, if this is the arm, this arm is having very low temperature because it is solidified, but this interface is having very higher temperature than even the melted temperature. Melt temperature is high, but the interfacial temperature is higher because of the supercooling. So due to which this dendritic arms spread their arm or dendritic roots spread their arm, but the liquid which is present inside it will also get vibrated at the time of stirring, and due to the vibration of this liquid, because this liquid is having very high temperature with respect to the solidified dendrites, and the dendrites are just nanometer in dimension. So due to the stirring effect of the liquid which is present interspatial in the interspatial spacing, they can just knock out the dendritic arms. No, the arms are so thin that the liquid infiltration in the interdendritic arm spacing can lead to splitting of the arms under suitable condition. Obviously, the liquid amount is also important. It's like if the spacing is very less, then it cannot happen. But if the spacing is high, then a lot of liquid is present in the spacing. Now, it can split. It can play a important role in the splitting.
Yes, ma'am.
Okay, because the volume of this arm and the volume of the liquid which is present in between, there is a huge difference. So the volume can play the role or the dimension. Yeah. So I think it's clear. Okay.
Ma'am,
Yeah.
ma'am, a question है. In previous class, you told about the composition. If the composition is changing, the interfacial temperature means the temperature at the interface depends on the composition, how the composition is varying when we are going for solidification process, right? So, can you tell me, ma'am, what you told about the distance from the interface in regards of composition and
No,
temperature?
composition is not playing the role. I think, okay, let me think. I think you can say, because if this is what the solidified portion, this is one the protrusion, and now it's growing, and after some time it's just spreading its arm in both the side, and this spreading of arm can only take place when the interfacial temperature and the melt temperature, there is a huge difference, and this difference will be created due to the composition. And this composition, if due to composition there is a huge temperature difference, this temperature and now this temperature difference is creating this arm. So yeah, technically, you can say it's relative, though although it's relative, but you can say the composition also plays an important role in the arm spacing and arm spreading.
Ma'am, actually, we are taking distance from the interface. Means which distance we are taking? Means the distance from the interface to the liquid zone, or what?
The
Means
interdendritic arm spacing na, this one, this दो आर्म के बीच में जो डिस्टेंस है, कि this is growing na, after how much
ma'am, ma'am,
growth it will spread its arm.
मैम जो आपने ग्राफ बताया था means distance from the interface and composition and again distance from the interface and the temperature.
हाँ, ऐसे
So
कुछ
if
था ना.
हाँ कुछ ऐसा आपने ग्राफ बताया था yes हाँ तो जो distance from interface जो आपने बताया था in x axis so what is that it is which distance it is the distance of arm
Okay,
spread or what.
distance, no no, इंटरफेस मतलब क्या होता है? इंटरफेस मतलब ये होता है, दिस इज द सॉलिड एंड दिस इज द डेंड्राइट, एंड दिस इज द डेंड्राइट. सो आफ्टर दिस इंटरफेशियल मीन्स इस पे, कि ये जो इंटरफेस है ना, ये इंटरफेस के कितने, मतलब how much distance the dendritic root is traveling, and after which it's spreading its arm, this distance. But the arm will not grow always 90-degree na, it can grow like this. So here the interfacial distance is 0, but here the interfacial interspacing between arms is more. I have shown you the curve where it's interfacial distance, मतलब ये इंटरफेस से लिक्विड का डिस्टेंस, जहाँ पे वो,
Which liquid
जहाँ पे ये
uh,
जो है ना, ये जो इंटरफेस है, ये कितने देर बाद ये आर्म स्प्रेड कर रहा है. It can like,
okay
it can look like
yeah
this, this, or this. No, that's what I'm saying.
okay ma'am.
And if this arm is having much more length, then it can spread its own arms as well. है ना? So this is all about the previous year assignment. There are a lot of current year questions as well. I have noted down. So today the time, no time has left. So I can discuss the current year assignment in the next class if you guys want. Otherwise, we can skip it. I think you are having the answers already. So if you have any doubt, we can discuss. Otherwise, we can go one by one questions as well. We'll see how much time will be there in our hand to discuss the current year assignment. So up to this point, if you have any doubt, please ask. No? If no, then it's fine. We can stop our class here. Thank you for attending.
Uh,
Yes.
Ma'am, if I am having any doubt after your
Yeah,
class
yeah.
is over,
Please
like
let me know.
so
I can.
can I mail you? If
Yeah, you can mail. I have shared the PPT now with you. At the end,
yes,
my
I
email
got your.
ID is given.
Actually, my research area is in the same, like that's why I joined this. And
Okay. Yeah, no
yes,
problem.
uh,
You can
and
mention to me.
actually you elaborated more means. Actually, we have some frequency that I can means mail means you can reply my answer because I have attended this class and means accordingly I will make my questions and I will put into your mail.
Okay.
So I think it will be easy for me further. So
Yes, okay.
that's what I asked. Yeah.
If I have any,
Okay.
if I don't have any of the answer of your question, then I can also get some time to find out and tell you in the
Uh,
upcoming class. Yeah.
yes. Yes. Actually, I got most of the answers in your class.
Okay.
Actually, because I am in NIT Jalandhar. Recently, I started my PhD. I think I am in your same batch. I think we started in 2022 July, right, ma'am?
Yes.
Yeah. So that's what I joined this course, and yes, this course is most useful for in my area of research.
Okay.
I think I got most of the answers from your lectures and the lectures which I have attended from NPTEL. So that's what I thought to ask this question because you are also busy, ma'am, in your work.
No,
But
it's
I
fine.
think if I will find some difficulty, I will mail you.
Yeah, you can mail me and can ask me anytime. No problem.
Thank you. Thank you.
Okay. Thank you so much. Okay. Good night. Bye.
Thank you, ma'am.